Thank you. Good morning. Excuse me. My name is Sungwoo Lim. I'm a senior lecturer at the Surrey Space Center in the University of Surrey. Today, I'm going to tell you about the development progress of our microwave heating demonstrator payload on behalf of our consortium. So we believe microwave heating method combined with 3D printing is one of the most potential methods to enable lunar construction and resource extraction. So to prove our hypothesis, we built a bespoke microwave equipment and also gas processing system. And using these systems, we did a lot of interesting experiment, and we were able to analyze the microstructure of the microwave samples inside against the various input powers, heating times, and also the different pressures as well, which was good. So we published our findings in the various peer-reviewed journals, including Nature Scientific Report. One thing missing is we don't know what happened inside the sample when you actually melting the sample. So to find out that, we actually did a computational simulation as well. Luckily, lots of lunar scientists already defined the most essential material properties for the microwave heating behavior of lunar regolith as a function of temperature. So you can actually see how the temperature trend change while the sample is heated. But one material property is called the dielectric properties, which is the most important properties to determine the microwave energy absorption. That's defined as a constant. So it doesn't really fully reflect the real condition there. But if you're looking at the lunar simulant side, just now I've talked about the lunar regolith. If you look at the lunar simulant side, the things are much worse. All the material properties are actually defined as a constant. So it doesn't reflect the real behavior at all. It doesn't show you the where and when thermal runaway occurs, and the temperature is just flattening or go crazy as well. So that's why one of my PhD students, Caroline, who's here, she's here, and she'll be analyzing and measure the dielectric properties of various different types of lunar simulant, trying to much improve our existing computational model. So her work will help us to optimize and complete the microwave heating process development, which is good, very good. And we also published this one. So everything is good, but there is one thing missing. Whatever we do here is everything is a simulation. The lab environment is simulated, and we use a lunar simulant rather than real lunar regolith. There is always small gaps between simulant and the lunar regolith and the real environment. For example, like a nanophase iron missing, and the highly electrostatic lunar dust effect and microgravity things. Those doesn't exist in our experiment, but we are quite sure those things are actually directly affect to the microwave heating behavior. So to complete our experiment, we have to do some experiment on the lunar surface, really. That is why we are currently developing microwave heating demonstrator payload. We are quite lucky. So since 2019, we are able to secure, it's small, but 5 consecutive research grants from the UKSA and the ESA. So we continuously developed our ideas and increased the TRL of our payload. The current TRL is about 4 to 5, depending on the subsystem. And the mass is just less than 20 kilogram, and the peak power is just less than 1 kilowatt. You might think, well, that's quite high for the payload. Of course, it is high, but because we have to deal with a certain volume of microwave cavity, and 250 watt is minimum input power, we can safely heat and melting the lunar regolith. And we are talking about the 50% of efficiency only with the microwave generator, which means we need at least minimum 500 watt of power supply needed. That's why the figures are quite high here. But obviously the model is not completed version, so we continuously improve and optimize. So figures will be optimized later on when you develop further. We hope to complete our development within 4 or 5 years and hopefully send our payload on the lunar surface to complete our experiment and develop the microwave heating process, sorry. So through the project, we continuously increase the TRL of each subsystems. So those subsystems include the microwave cavity, sample collection mechanisms, or sample handling and delivery mechanisms, and also oxygen extraction systems, etc. We also developed our own version of a 250 watt of solid state microwave generator. And we're aiming to have a DC to RF efficiency up to as high as 60% after space certified. So at the moment, we are in the almost finalizing the UKSA project, actually due to end of this month. What we've done for this project is we manufactured the prototype of microwave cavity and also microwave generator. This is a prototype of microwave cavity. We tested. As you can see from the plot there are two plots, two peak point. One is Lunar Mare simulant, in this case JSC1A, and the other is a Highland simulant, in this case NULHD4M. They have about 200 megahertz of resonant frequency difference. This is one of the reasons why we go for the solid state microwave generator, because we have to be able to switch the frequency in a single cavity design. So we've done some simulation as well with this current design. And what we found is, you can still see the red right here. It's red color here, isn't it? The red color is a high intensity of the electric field. The EF high intensity of electric field is actually outside of the crucible. This is a crucible. So that means the sample inside of a crucible has a less electric field and resulting in the lower heating performance than we anticipated. So we see there is still rooms for the improvement and also optimization. So we will address these issues through the next project. We also manufactured the 250 watt of solid state microwave generator. Our initial design is with one single PCB board over there. But when you actually manufacturing the prototype, we decide to have separate the blocks. So in that case, with this way, if something happens, you can only change one block or two blocks rather than completely remake the entire board. So that was a good decision. But also we found some difficulties as well. So small mistake can make a huge consequences, as you can see. What we found is when you tested this prototype, we found that there is a high impedance discontinuity between blocks, and that caused a huge burning and system failure. And we also found that we probably had to have a much higher power, reflective power circulated than we originally planned, because the cavity is generating reflective power, quite high reflective power in the beginning. And we didn't realize that, which means we also need to have a better thermal management mechanism as well. So we will also address these issues through the next development, through the next project. Anyway, because we said that we have to remake it, so we instantly make the blocks, and this time we the low. So now we can actually keep the net in the so again, yes, this is a kind of a course and we continuously try to increase the next project. So our final goal is actually trying to develop microwave heating-based 3D printing platform to enable the lunar habitat and infrastructure construction, and also extract the oxygen, water, and the metallic element as a byproduct. So when I say byproduct, means when you heat and melting lunar regolith, if you add some chemical reactions, you can extract the oxygen, and also you can beneficiate the metallic element as well. Anyway, that's a quite hard task. So instead, we are developing everything from scratch. We intend to leveraging the existing work from our payload development. So what you're looking at here is a schematic diagram of the payload, our MHD payload. We will add the 3D printing subsystem over there. So that makes it much easier, so we can just reuse the systems. We also intend to expand the functionality of the payload. At the moment, the payload intend to melting the lunar regolith and measure the volatiles and also extract the oxygen from there, just like ESA's PROSPER work, but with a more large scale. So our sample, each sample is 50 grams, much larger than PROSPER one. But we need to extend the functionality further to be selected as one of the technology demonstration missions, probably. So one of my PhD student, actually former PhD student, James Cole, who will talk right after me, he actually developed on how to extract water and measure the or how to extract and measure the water from the ice regolith. That's quite an interesting idea. So we want to add that functionality to our payload. So in that case, we can send our payload to the PSR if possible as well. So such that if we continuously expand our functionality, obviously we need to expand our consortium as well. So initially we formed with the University of Surrey, the Open University, Added Value Solutions UK Ltd, and also Wi-Fi RF. But now the Allen University in Germany and the iSpace Europe also joined our consortium. So we hope to develop our microwave heating based 3D printing platform within, this one is maybe within over 5 years or 10 years. And eventually we build a lunar habitat on the moon surface. So if you have any interest in about microwave heating related scientific investigation or engineering activity, please do contact us so we can discuss potential collaboration. Thank you.
Thank you very much, Sungwoo. Are there questions from our audience this morning? Yes, please.
Is it Sumasan? Hi, Carl Hibbs again, APL on Lunar Surface Innovation Initiative. Interesting talk, very nice talk on microwave heating. As you pointed out, the absorption of the microwave energy is key to it. And the question is, how does the composition of the simulants affect the frequency that's used for absorbing the energy, you know, the specific excitation energies? I know it's a difference between the JSC-1A and the Highland simulant. I'd like to understand why. And also, simulants are different than the moon. They actually can have molecular adsorbed water on them. Would the presence of adsorbed water affect the absorption of this microwave energy at all?
Yeah, so the chemical composition is the difference between the Mare and the Highland regolith or simulant. The chemical composition is basically mostly we are looking at is contents of ion element. So there are quite different between ion contents. And initially we thought, and everybody, like including Lawrence Taylor, who was actually the first person who put the real lunar regolith in his microwave and burnt it and found, well, Eureka, we can do that something. Since his experiment, a lot of people actually expected maybe Mare regolith and simulant is better chance to absorb the microwave energy because of the high contents of the ion element. But it turns out when you do this lab experiment, actually it's not really the case. Both simulant can melt it quite well. But what I can tell you is that the resonant frequency difference is based on the, I believe, the ion element contents. And the second question about water contents, obviously there is differences between lunar regolith and simulant. So before we actually do the experiment, we desiccated the sample in a vacuum oven with a 200 degrees Celsius and leave it for more than 72 hours and try to get rid of all the moisture first.